Hi everyone, I'm Marvin, and this is the third part of TCC's Cloud Load Balancing Architectures. Now if you just bear with me a second, I'll just expand the screen. Right, okay, so at the end of part 2, we talked about ADC deployment at the network edge. We discussed topics like global load balancing, DDoS mitigation, and obviously physical appliance-based ADCs. Now, we're not going to talk about that in this part, but if you want to catch what we discussed, please check out part 2. So before I start preaching to you about what VADCs can offer over traditional ADCs, I want us to very quickly go over some of the drawbacks you might find with traditional ADCs, especially when we move to Tier 2 services. Tier 2 here is simply services within the data center. But that isn't to say that VADCs are right for all Tier 2 services. On the contrary, they're not always the way to go, and that's what I want to show you. First of all, let's consider the network design being depicted here. So this is based on a Juniper core. Now, it could just as easily be a Cisco core or even an Arista core, So there's a number of ways we could have gone here, but we chose Juniper to illustrate what we're trying to say. So here we have a modern pod design centered around a spine and leaf model. Okay, that's your spine and that's your leaf. More on that later. So, spine and leaf model, which is actually quite different to data centers of old. Well, I wouldn't call them old exactly. I'll just call them tried, tested, and true. A model most architects will swear by, where you had traditional layer 2 domains spanning multiple racks and a number of access switches. Another common practice with these older designs were redundancy protocols like HSRP and VRRP, which I'm sure you're all quite familiar with. Well, today's modern spine leaf pod designs mostly do away with all of that. I know what you're thinking. It sounds crazy, but it really has made cloud computing what it is today. Now, I will touch on how this is done to an extent a bit later on, but future sessions covering data center design and overlay technologies will really get into the meat of how the data center has changed. Now, one of the key things a spine leaf architecture helps to achieve is a multi-tenant network. Obviously, this is something I'm sure all of you with cloud computing experience are very aware of. But achieving multi-tenancy in itself can pose numerous challenges. We have a number of prerequisites like traffic separation, common services, extended workloads, VM mobility, and so on and so forth. But none of this is achievable without an appropriate network design that can provide what we need. So what does this new spine and leaf model really consist of? Well, first of all, the links between the spine and leaf switches are all routed layer 3 connections. So immediately, we know we can't carry native layer 2 past local access switches. Right, so let me show you what I mean. So if I go back here, right, so if we assume an older, let me not say older, a previous model where you had your access switches here and your distribution layer switches here. And we have our racks here, okay, which is where the access switches connect to. What would typically happen is all these access switches will carry all their VLANs or layer 2 to distribution switches, which will be interconnected everywhere. So you could have a subnet or even a VLAN that could span all of these, because what you had was the distribution switches connected to every single one of them. And let's say you had VLAN, I don't know, VLAN 20 here. VLAN 20 could easily be carried across here because this carried native layer 2 to distribution. And obviously your distribution switches had redundancy protocols like HSRP or VRRP, but for the sake of VLAN spanning racks, it was quite simple in the older model, okay? But when we talk about the spine and leaf model, and we say things like layer 3 is carried down to the access switches, immediately what does that tell you? We can no longer natively carry those VLANs, which is why I made the statement that we're now contained, which is what we are. We're contained, and we can't carry native layer 2 past local access switches. Now, I guess this could work for small scale deployments. And when I say small scale, I'm talking about when we have a number of servers within a rack, and only those servers need to be in the same VLAN/subnet, okay? But the minute we start having larger deployments where they're spread out, then it becomes more difficult, okay? So as I said, it could work for small scale deployments, but when we do start looking at huge cloud topologies and VMs in general, it just doesn't cut it. Especially with the ability to move VMs at will based on usage. VM mobility, something like that. That model won't cut it. This is where overlay technologies come in. They carry our good old layer 2 frames inside layer 3 and transport them across the network. But the good news there is that all the protection you get from layer 3 to prevent infinity loops, the things like TTL, etc., they're all present here when you use overlays. And there are other benefits, such as no requirements for VRRP, etc. Now, there are quite a few of these overlay technologies around, but I won't get into that here. We've got another session for that. Instead, let's assume VXLAN, which is pretty popular. Yeah. So let's assume VXLAN is being used to extend layer 2 between racks and even data centers, right? Because you can do that too. But what exactly is VXLAN? Okay, I'll provide a 20-second answer, or thereabouts. But I promise to go more in depth when we get to the SDN sections. So VXLAN began life as an IETF draft by Arista, Cisco, VMware, and a number of other vendors. It's an overlay technology that can bridge multiple layer 2 domains together over a predefined underlay network. Underlay here is your typical layer 3 routed network with any of the classical routing protocols we all know and love, such as OSPF, BGP, etc., etc. Another great thing about VXLAN is its ability to scale past the 4096 limitation found in the traditional .1q VLAN namespace. In fact, the 24-bit VNI in VXLAN can allow for up to 16 million layer 2 segments. So you can see why it's a favorite for many cloud providers. Right, okay. So if we now go back to our ADCs, okay? Let's go back here and talk about what we've been trying to say. In this instance, our ADCs are all centralized, okay? So here we go. So we've got ADCs here and ADCs here, okay? And they're serving each of our tenants and the internal applications. So here are our tenants, tenant A, B, C, and these are applications within the tenants, okay? Naturally, we'll have different sets of load balancers per data center. So a pair in data center 1, a pair in data center 2. And we'll also have our GLBs. So here you go, you've got your GLB here, and you've got your GLB here. Quick note, these GLBs obviously are not the same ones serving our external internet-facing customers, but they're completely different GLBs, okay? Now the GLBs will be doing what our external counterparts are doing. They'll be manipulating DNS responses to direct traffic appropriately to both data centers. All looks good, right? You can do all the cool stuff we talked about with the external load balancers here. You can do stuff like SSL offload, caching, Wi-Fi protection, all of that. So what's the issue, you might ask? Well, nothing really. I mean, this model is how many existing data centers deploy load balancing today. There are some caveats though, such as symmetric routing, to make sure all return traffic goes back to the load balancer and not just straight to the client. So techniques like source NAT can help there. But now and again, some applications might need the servers to see the true source IP address. Don't get me wrong, there are ways to have the source IP address included, even when you do perform source NAT, but these have their own prerequisites. Much too many to discuss here. The point is this: standard centralized ADCs are just not as optimal when dealing with multi-tenancy, layer 3 pod designs, and the general advancement in today's data centers. Right, so if we look at this Juniper core once more, just to understand everything going on down here, okay, we can see multiple application stacks, okay, across common tenants. Now what I mean is, so if you look here, we've got tenant A, okay, we've got tenant A here, but we have application A and we have application B, yeah? You've got tenant B here, they're both tenant B, but within tenant B, you've got application C and D, okay? And obviously you've got their counterparts in the other data center. Naturally, in a much larger environment, you'll have lots more applications within the tenant, okay? But you get the picture, okay, of what we're trying to say. Now, if we wanted to achieve improved application awareness, an option will be to deploy our ADCs as close to the tenant network as possible. But traditional ADCs will be overkill for this, especially if we're looking at predominantly VM farms. This is where VADCs come into the equation. If we did do this, we could immediately see lower latency, possibilities for the vertical scaling of the VADC CPU, and other things like memory. Okay? Now, if we just had a quick look at this, this is VADC deployment per tenant. So let's quickly talk about what's happening here. Okay? So previously you saw tenants and applications. Now, if we look here, we've got tenant A. Within tenant A, we've got app A, app B. So again, you could have a much bigger deployment with lots more apps. But the point is this here. We no longer have our centralized ADCs here, as you can see, but we have VADCs inside our tenants. So this is what I mean by moving them a lot closer. They're deployed on the same hypervisors as our application, okay? And you have it here as well, tenant B. So you've got app C, app D. Again, in the real world, we have a lot more apps. So you have your VADCs here and here. So these are more distributed VADCs per tenant rather than centralized, okay? But where would this model work? Shared services, that's where. If we think about this, a large number of cloud-based VM farms are based on shared hypervisors across a number of different applications, with the tenants used to form partitions based on service groups or functionality. And another benefit, change control. Even with automation, changes are always better when contained wherever possible to the tenants that require them. This model allows for that, something you can't say about centralized ADCs. Now, the beauty of most VADCs out there is that not only can you deploy them as virtual appliances and hypervisors across the shared tenant network, but you can also stand them up on general commodity servers, practically standalone. But I know what you're thinking. That is practically what a physical ADC is, right? And you have a point, which is why VADCs as virtual appliances are really what this model calls for. But is that it? Can VADCs then sort out all Tier 2 service requirements? I'm afraid not. What about platforms like mainframe, for example? Now, in theory, VADCs can distribute load wherever you want them to, regardless of where they are, okay? But the benefits for platforms that don't support them, like mainframe, it's just not there. There's no real benefit to have a VM on a VM farm, then load balance into a mainframe, probably somewhere completely different in the network. Okay, benefits just not there. So it's for these reasons that the centralized ADCs can't completely go away. I guess the moral of the story is that both types of ADCs have their use cases, especially as the industry starts to move towards VMs, while still maintaining a large amount of services on platforms that might not be able to leverage the true capacity of VADCs. And that's it for this part of the session. If you'd like to get all the parts that make up this volume, please purchase the complete pack from our website at www.tcc-plc.co.uk. Thanks for watching.